Hi, everybody. Welcome back to another Future in Space Hangout. My name is Tony Darnell from deepastronomy.com, and these Future in Space Hangouts are brought to you and sponsored by the American Astronautical Society. If you go to astronautical.org, you'll be able to check out their website and see all the cool things our members are doing. But you don't have to do that now because we're going to do it right here. We're going to learn about what some of their members are doing during this hangout. And just before I go live, you know how it is when you push the go live button. Well, maybe you don't know, but I'll tell you, when you push the go live button, right before that, everything seems to go wrong. And right before I go on, Shantanu sends me a little chat here that says communications is spelled wrong. Okay. So anyway, we are going to be talking about optical communications, not communications, for developing a cislunar neighborhood. And it is a great day in the neighborhood because anybody who's watched my streams for any length of time knows I have long been an advocate of getting to the moon first, building the infrastructure that's required and the experience that's required to get to the moon and to live on the moon, to communicate on the moon before we go to Mars. Let's go to Mars. Sure. Let's send some people there and then come back. But let's do all of this. Get some experience first. The moon is only a few days away. Apollo rocket style, and we can get there quickly, and we can do a lot of other things. We're going to talk about the communications aspect of it here in this hangout today, in particular optical communications. So I'm going to introduce Shantanu Gupta. He is the chief engineer for optical communications at Aerospace Corp. He's going to drive this hangout for a little bit and get the information out to you. I will be monitoring the chats on Twitter, Twitch, Facebook, YouTube, and also on the American Astronautical Society YouTube channel as well. I see and look at your chats, and when the time comes, we'll ask questions. If you don't have any questions, then I'm going to ask mine. So get ready. All right, so let me bring up Shantanu. Go ahead.
Yes, hello and good afternoon, all of you who have joined. First of all, just want to continue on the same enthusiasm and theme that Tony started. Thank you, Tony, for that. Just when you were thinking of, there are really no places to go off the grid, I mean, connection-wise on the Earth. Okay, we are trying to figure out, if you were thinking about it, okay, eventually we'll go to the moon and I'll be off the grid. Well, we're trying to figure out that you can't really do that. So we'll be talking about that. And so on the more serious note, I'm Shantanu Gupta. I'm from Aerospace Corporation. Just by way of introduction, for those of you who don't know about Aerospace Corporation, we are a federally funded research and development corporation, FFRDC. And more importantly, we are the trusted agent for all this US government space agencies, both on the civil side, NASA, NOAA, for example, all the DoD side, for example, Space Force, and as well as all the intelligence community. And clearly, we can't really talk about much of that. Having said that, I'm actually very excited to have two of our panel members who will be sharing their thoughts, and I would like to introduce them. So first of all, David Israel from NASA. He's the chief architect there of all the space communication and navigation program. He's going to be talking and sharing some of the thoughts, and as well as showing some really nice slides and cool animation what you'll actually see when you go to the moon. And right after that, we'll have Bob Brumley join us, providing more of the commercial perspective, his thoughts and Comstar's perspectives on how we can leverage the cislunar neighborhood.
Shantanu, I hate to interrupt you, but something's happened to your mic.
Oh, sorry.
Yeah.
Hello? Can you hear me?
Are those earbuds?
No, it should be okay.
Oh, there you go. You fixed it.
Okay.
All right.
Sorry about that.
Sorry, I had to interrupt there. Continue.
Okay, no, I appreciate it. Thank you. And so we'll have Bob Brumley go after that and sharing his thoughts and Comstar's vision of how you can actually leverage all the communication and compute environment in the lunar neighborhood. So with that, let me first introduce you, David Israel from NASA. David, the floor is all yours.
Are you is your mic, are you muted? We can't hear you.
Oh, we're off to a great start. All right.
Communications is spelled.
Communications.
So was neighborhood. Neighborhood was
Yeah,
also spelled wrong if you're from the Europe. Anyway.
So I'm as Shantanu said, hello everybody. I'm the division architect for the division at the NASA Goddard Space Flight Center, where we are the home of the Near Space network. So that's people might be familiar with the TDRS constellation and the ground stations, where we support the International Space Station and the Hubble Space Telescope and lots of many missions. So my job as the division architect is I get to help dream up what the future architecture should be for the places that NASA wants to go. And one of them, of course, right now very busy dealing with planning for the moon and then to Mars, as was mentioned. And I'm also the principal investigator for the laser communications relay demonstration. So that's what this illustration is right here behind me. It's a payload I'll give you a little bit more information about, but this was launched. It's on board the STP-6 spacecraft, launched on December 7th out of Florida. It is now in geosynchronous orbit, and we're going through the checkout, and soon we'll start experiments. And you also see in the picture of the space station, there's another project within a year's time or so. We should have the payload on board the International Space Station that will be able to communicate through LCRD. So I guess we can bring up my my slides, please. Okay, go ahead to the next slide, or if you bring up the first animation, I guess. So what you'll see is the our LCRD is it's a payload. It's got the two optical terminals. Folks can see that. There we go. So there's two terminals that are mounted onto the spacecraft. So those optical terminals are about 10-inch diameter, and they're two independent optical systems. So with bidirectional links and switching hardware in between, so it allows us to relay data at our data rates that we're have on board. It's 1.2 gigabits per second is the maximum data rate, and we have two ground stations, one in Hawaii and one in Table Mountain, California. And the data rate, which I'm sure you'll hear more as we talk today, that 1 gigabit per second by optical is by no means the max that's going to be possible. But our main objectives for this experiment, a lot of them are about characterizing the atmosphere and the weather performance and how to do things, optically from this space to ground link, as opposed to cross links in space. So if we go to the next animation, there's some really good artist view of let's see. You'll be able to see the.
Hang on, I think you did you load it up, David?
Oh, when hang on. I think it only let me load one at a time.
You can only do one at a time. Yeah, sorry about that.
Okay, coming soon. Okay. Okay. Here's the other one. That has a nice view, because you can see the full spacecraft, and there, for artist purposes, you can see that on the other side of the panel we're mounted to. We have two modems. Those modems are large. It's actually older technology. We started this program 10 years ago, so things have really changed. If you can show it again, I just kind of loop it a little bit. So what you'll see there's two modems, and each modem has two chassis to it, and then there's two switch units, a prime and a redundant unit. And then each optical module, the telescope there, has its own controller electronics box that takes care of doing the pointing and the pointing acquisition and tracking. So if you can go ahead to the next slide. So we launched in December. we're checking it out, and this project is designed to be an operational demonstration. So in 2013, there was the Lunar Laser Communications Demonstration, LLCD, that flew on the LADI mission and was very successful. So that was really the technology demonstration that this technology can work. And it was a short-lived demo because our host ride was the LADI spacecraft that intentionally part of its mission was to crash into the moon and stir up some dust. So we lost our optical terminal as part of that. But it was highly successful. And LCRD now we're on a GEO spacecraft, and we have 2 years experiment time. The payload is designed to last longer than that, but 2 years is our primary experiment time, where we're not committed to any missions or operations from the beginning, so we can set it up to do all sorts of emulations and characterization and different things to help learn how to operate optical links in an optical relay. So there is a might not be in the slides, but I'll put in the chat perhaps, or pass on there, or you can Google to find the LCRD website. And we have a guest experimenter program, so people you can propose experiments, anything from bringing your own optical modem if you have such a thing, or just part of the atmospheric studying, or actually quite a bit of the experiments will do like network protocol and networking tests to run things over the optical links. So if people want to understand or demonstrate performance going through the atmosphere on an optical link. So that's LCRD, and we have mission T-Bird that's scheduled to launch. You see that we're in this upcoming stretch where there's T-Bird, which is a small payload on a CubeSat that's going to be able to transmit 100 to 200 gigabits per second from low Earth orbit down to a ground station. The Illuma-T payload is set to launch and get installed in the GEM module of the International Space Station. And at that point, then we'll have something in orbit that we can do our LCRD demonstrations with, and then we'll evolve. It'll be connected to the space station data systems, and the plan is to evolve it to be another operational communications path for the space station. There's the DeepSoc terminal, which is flying on the Psyche mission that's going to the Psyche asteroid. So that's a deep space, a much farther distance. And then when the humans go to the vicinity of the moon again for the first time in 50 years on the Orion Artemis 2 mission. So this is not when they land, but when they go around the moon and then come back. There'll be an optical terminal on board that mission. And so when we're all watching the HD video, when that happens, that'll be coming to us over the optical link. So go to the next slide, please. Okay, so talking about the moon, so I've been very involved. We've been working on what we call LunaNet, Lunar Network, and you can substitute to kind of check the sentence or the usage if you use the word internet instead of LunaNet, then it should still make sense. So, for example,
I love it, LunaNet.
Yeah. So there's no. The idea is that there's no kind of owner of the whole LunaNet. There'll be different LNSPs, we're calling them, LunaNet service providers, that will basically be able to work together to put together the infrastructure that to support the users. So of course this is really going to leverage standardization. We want commercial partners, international partners, everybody else. The idea is that like the terrestrial internet, there'll be to make it kind of cooperatively built up infrastructure. to give all of the services that all of the different users may need. So one thing that picture on the right-hand side is attempting to illustrate is that the standards and the things that we're pursuing for LunaNet is that we want to make sure that we're doing things that don't break when we try and do it at Mars. So we really are looking at how we are setting the standards and what we're doing so that it's not for the moon only, but we can duplicate it at other planets. And if finally the last slide is just showing, so the picture in the middle is the one we used in our original LunaNet presentation, just to really illustrate this this analogy that we want the lunar explorers to start to be able to have the same kind of ops concept that we have on Earth, where you can be connected and to different data sources, and you can have the applications that such as what you have on your phone, where you have the GPS on your phone, so you know what time it is and you know where you are, and then you have the data connectivity so that your phone can go out and grab data that's relevant to where you are and what you're doing. We want to enable that same thing on the moon and around the moon as well. So besides the communication services, there's the position, navigation, time services. The detection and information services is like space weather alerts, and then science services would be using the links themselves to kind of do gravitational mapping of the moon or whatever the body is that you have. So if you think of what we have at Earth as kind of like the same model but EarthNet, then the network communication services would be all of our mobile providers and terrestrial data providers. The PNT service would be the GPS. The detection information services equivalent would be like the National Weather Service, maybe, that collects the data and then sends out the alerts. And then science services, I assume there probably are some scientists that are using our terrestrial communications links to do some kind of a study. So all these pieces together are really to enable things that we're hoping, and we're designing it because we want to enable things that we haven't thought of yet that people might want to do on the moon. So we've been working very hard not to limit ourselves to say, well, there's only going to be 3 things launched, so we can kind of hard code things or do things in a sort of self-limiting way. So we're trying to keep it very open, and I was able to get a preview of Bob's presentation, and I was excited to see it because to see that interest, and it really maps to what we've been seeking for LunaNet. So that's it for me.
Okay, thank you, Dave. Tony, I just wanted to quickly check with you just to see if there's any direct questions for Dave. I know we will come back later, but I just wanted to check with you if there's any questions. And
okay, sure. Yeah, hold on here. I got a couple. Here's one from Dimitri. I'm sorry, Dathri Samavarapu. Are there any plans to demonstrate this for satellite-to-satellite links?
So yes, in for LCRD is designed to be able to track LEO spacecraft, and in our initial case, we don't have anybody flying that we can communicate with. But once the space station payload is up there, then we'll have satellite-to-satellite links, and it's a little different. It's like a relay service link, so it's a satellite-to-satellite link, but it's a little different than other things that you've probably heard about, where it's more cross links of constellations of spacecraft sharing data as a cross link. This is more like a relay service provider using an optical link to support satellite users.
Okay, and Jim wants to know, David, what, if anything, was learned during the LADI mission's laser communications demonstration that could be applied this time around?
Okay, well, besides don't fly your payload on a mission designed to crash into the moon, maybe the first one. But I would say the second one.
You're gonna what?
So so really, there was a lot of questions about whether pointing acquisition and tracking would work, and how fast would it take, and being able to see how quickly and how well that worked really gave a big boost in the confidence that then went into the design. Some of the particulars of the optical module and controller electronics software and the pieces are have heritage back to that mission, and then also part of what we learned about looking at the weather and predicting which ground stations would be the best one to use. Also, we're building upon that as well.
Okay, and Chris wants to know. This will be the last one, that we can move on. Where did Bob go? Okay, I'm a bit late, but Chris wants to know: are the two modems capable of phase coherent operation?
Yes. So the modems operate. We're demonstrating two types of modulation. So one is pulse position modulation, where you don't need to coherently track the signal. It's you're counting the photons, and when the photons arrive. So that's a technique to be used for they call it like photon starved situations that'll be particularly important for deep space operations. But then we're also using a differential phase shift keying, DPSK, where then the as a phase shift keying, then it's a coherent type operation.
Okay. Do you want to do one more, Shantanu, or do you want to do?
Yeah, I think let's wait and let's go to
Okay.
Bob's, and then we'll come back, because it is supposed to be a hangout, so we will be discussing further. So we're delighted to have Bob Brumley join us, and as I mentioned, he's going to bring the perspective from Comstar, from commercial operations, and quite a bit of a unique perspective of the whole enterprise kind of approach. What is driving all the needs for communications? With that, Bob, feel free to introduce yourself, and the floor is all yours.
I appreciate it. I am the chairman and founder for this company, Comstar Space Communications. I'm also the CEO of a sister company called Laserlight Communications. And I'm really excited about how Dave was laying out the evolution of the LCRD program, because we're always one step behind where NASA is. NASA pushes it out, and then we come in commercially behind them with our vendors to pick that up. And a good example is Laddie. We formed Laserlight in 2012, and Laddie was a success.
Bob, your sound cut off.
Which allowed me to tell not only my vendors. Can you hear me?
No.
Now you're back. Yeah.
There you go.
Okay. All right. So we follow behind NASA, and NASA has been pushing the envelope on this for now 10 years, as David pointed out. Excited to see where it's going to be going with respect to the moon. Cislunar. Let's start off with the commercial standpoint. Real estate really is the key driver on how you put a business case together, how you design your architecture, and how you provide services. So to a certain degree, and I will do this myself.
Yeah, he does not have a good internet connection. We have to work a lot on Earth-based communications.
Here we go.
As well.
I will shift over. Can you hear me? No?
Yep, we got you.
Okay. While we're doing
you're
that.
There.
All right. This picture really is just trying to give you a feel for what the environment of Cislunar is. It's 240,000 miles from the lit side of the Earth, and so in a sense you're in it, you're through it, you're not above it, you're not below it. You move the other side of the moon, you can basically be in translunar. But this is a unique environment between the moon and the Earth. Where Comstar is situated is at L1, It's one of the stable points with a line of sight between the Earth and the moon. And that allows it to see activity on the near side of the lunar surface, either around it or on the ground or on the lunar surface itself. It also gives it connectivity opportunities to satellites such as laser light and also other satellites, even the ISS, where it can connect either RF or optical to that infrastructure. And then it can then also relay and go to the ground, which then gives you what we call in telecom an end-to-end structure. So you have the ability to tap into traffic, both RF and optical, in this environment, and then move it into what would be the existing infrastructure. And as Dave and NASA want to build the infrastructure up on the surface, so that there can be Lumen, Orange in Europe, Equinix, et cetera, and opening up AWS, IBM, opening up the ability to serve the moon. So that's really Comstar's mission. Comstar is a network. Back in the day when we created the internet, we had what was called network access points, and a network access point, or a NAP, was basically open to everybody to connect to. So as with this picture, Comstar, if you can see the lit side of the Earth, and you're sitting on a lander on the moon, then you can see Comstar. Relay, use it as a booster of your signal, use it as a content delivery network to the Earth, or use it as a data center, or use it as a compute center. Compute is going to be critical to what would be industrial development on the moon. So looking back to the infrastructure on the moon itself, I imagine these signals, these antennas off to one side, to the left or to the right, would be LunaNet participants. But then hauling what would be low latency, forward store, command and control signaling for robotics, so that you can actually do scale robotics on the lunar surface for industrial development, mining, etc. That's going to require a strong signal within 200 to 300 milliseconds of where you're delivering the service. You're not going to get it from the surface of the Earth. So you can't do remote command and control from the Earth and run next generation compute robotics. You have to do it either in orbit around the moon, and then you have the on again, off again line of sight problem, or else you have to do it on the lunar surface, which is what the future of LunaNet would be. And in the interim, that's what Comstar would do. And Comstar is designed essentially architecturally to take advantage of some of the developments NASA has already brought forward. It is a hybrid satellite, meaning, in other words, it's going to run RF, and it also will run optical. On the RF, it is filed for a significant number of RF frequencies, so it can pull in any number of frequencies, RF frequencies, to its base, which is moon, lunar to Comstar. Then the intention would be, if it is high capacity, high throughput RF with a lot of volume, we'd convert it to optical, and then we would send it optically on lasers to the Earth. In addition to that, that provides what would be scale connectivity. But customers want content. That streaming that Dave mentioned about around the HD streaming about going around the moon on Artemis 2, customers want that. They want to be able to show content. They also want to be able to deliver what would be large gigabit packets and also petabit packets, and do it in such a way that it can stream through that infrastructure I mentioned earlier into what would be the main infrastructure on the Earth with a minimum amount of middleware and service handling. So by keeping it always on, always available, by making it cloud-based as a data distributor, what Comstar is basically a data center until data centers can survive on the moon. It's a cache and store and compute platform until cache, store, and compute can be deployed to the moon. It is a data relay system, and it's also a host. And then through the partnerships that it has that I mentioned earlier, it allows it to serve particular customer profiles. And one particular profile, for example, would be lunar orbiters. We expect those to be the predominant player on the lunar surface for about the next 5 or 6 years in one size or another. In around 4 to 5 years, we think what's going to happen is it's going to move into data management services, not just data relay. And that would, in fact, allow for a broader use of low latency data management, industrial development, settlement, if you will, extraction of minerals, sustainability of activities on the lunar surface, and ultimately in partnership with LunaNet partners. And then it's there for 15 years. So it's got a stability to it, not only as its location, but also the time it's going to be there. So it's going to serve as a logistics hub in addition. And the logistics hub can be doing things not just between the Earth and the moon, but those transiting from the Earth to the moon. It can do TT&L, tracking, tagging, and logging. It can look not just at the moon, but it can look either side of it as well as either side of the Earth. So situational awareness. It can serve as a massive PNT beacon, just one step, almost like a TACAN sitting outside the lunar surface. It can also be a platform for renewable payload stationing. And then finally, it's built for growth, the capacity of the satellite. So in sum, I think we kind of go back to where we started here with what NASA's been doing and NASA's plans relative to the lunar surface as well as around the moon. The private sector is looking at step-by-step building off that development and then going its own way to develop systems that not only serve other private sector companies, but also serve NASA's needs and ESA's needs when it comes to what would be robust communications in Cislunar. Let me stop there.
Yeah, thank you very much, Bob. I mean,
Your mic again. Sorry.
Hello? Oh, can you hear me now? Can you hear me? Okay.
Yeah, it just still got a lot of noise in it.
Okay. Okay. Hopefully you can hear me better now.
Yes, that's better.
Okay. So first of all, I really appreciate, Bob, the whole end-to-end perspective and the architecture and how you have put the whole thought together and all the pieces as built together. It's not going to be done overnight. So it's very great and refreshing to see, and also very refreshing to see some of you're touching upon engaging with other partners across the globe. So most likely we'll probably have some questions, Tony, but I want to probably start with a question, a general question directed initially to Bob, and then of course Dave's viewpoint on that. From an overall perspective in the commercial sector, Bob, you just touched upon it in one of your slides, some of the other partners that you're working with or framing the architecture. And also on the agency side, Dave, what about the participation with other entities, European and elsewhere? Could you elaborate on that, Bob, a little bit more and how it's been going? And then perhaps Dave can also address it from the agency perspective.
Yes. The moon is really interesting when it comes to early partnering. NASA has, as does ESA, have a responsibility for their own missions, but also to serve as sort of the organization activity that the private sector clusters around. You have early stage companies like Pathfinder, which is Surrey Satellite, funded by ESA. You have Moonlight, which is going to be right around after Artemis 3, which is a constellation around the moon. You have Harmony, which is CubeSats, which are privately developed that want to basically orbit the moon and do low-level mapping of the lunar surface. I mean, these are all real companies that are spending real money to do this. But Pathfinder needs a customer because they're a communications relay satellite. Comstar doesn't see the far side of the moon. Pathfinder does an elliptical orbit around the moon. So Pathfinder can be a customer of mine, but I can be a customer of Pathfinder's. In addition, so we're all, this group is not a group of aspirational PowerPoint projections. Everyone's trying to work together to see how we can develop each other's business cases. And NASA really has done something that it does not get any credit for. And that is the most significant thing it has done relative to the moon. It's not so much Artemis, but it's the CLIPS program. Because the commercial lander partnership is a partnership for decades worth of cooperation with NASA by the private sector. And if you don't know what it is lunar landers where you have a commercial partner like Astrobotics, Intuitive Machines, or Maston. Through a Space Act agreement, NASA agrees to be a partner with this private company that then it takes the capital risk, but it has an anchor tenant. And then it can go out and sell payloads on that lander for a durational flight, 8 days, 7 days, some period of that. Those landers are getting more sophisticated. The partnerships are getting more specific. You're looking at possibly extraction of minerals with the landers, a whole variety of services these landers are starting to explore, which creates a business economic base. You have to ask the question, that's what the bankers do. Why are you going to the moon? If you're going to the moon to sell NASA services, that's subject to budgets. But if you're going to the moon to do other things that you can self-sustain your business without NASA services, which NASA wants you to do, they want to help, but they don't want to be basically an anchor tenant of you forever. If you can stand alone, then you have to figure out what is your line of business. And our view is that's happening now, and a lot of it is driven by CLIPS.
Yeah, thank you, Bob. That is an excellent insight, and hopefully for all the audience also, maybe just a few minutes, Dave, your perspective on this international kind of cooperation, and then I think we'll look at some of the audience questions. Tony?
Yeah, and I agree with what Bob said, and it's certainly true that NASA, ESA, all of the government agencies. We don't want to be our own providers, right? We're trying to do what we are able to do to put the standards in place and be those early anchor tenants. But we really want the economic case and the business case to boom, such that we are just another customer or set of customers that's then getting services commercially from the CLIPS provider that will put your payload onto the surface, and from the communications provider that will get our LunaNet service from, for example. And then in that way, we and sort of going back to the internet analogy that we've been really using from LunaNet, right? It can start as a government thing, and it helps to get it propped up and have the standards happen. But really, once there's clear get over the hump and the commercial market is there, then it can really take off and propel it itself. And that's what we're looking to do. It's very encouraging. Just the difference from I was involved in the constellation program in like the mid to late, like 2005 to 2010 sort of time period, and just and then when there's talk about commercialization and providers, then it was pretty easily dismissed as being an option at the time. But the world has changed so much, since then, that now we'll look and work with the other agencies to do things with the government agencies when we have to, but we're really trying to encourage and support and enable the commercial providers as soon as we can.
Okay, yeah, thank you, Dave, for that insight. Tony, I mean, any questions from the audience, either for Bob or for Dave? And
yep,
we'll have a place for them. So
yeah, I want, since I got the mic, I want to do one real quick. So I was at a Glenn Symposium a couple years ago, and the keynote speaker there from NASA was making the point of a lot about what Bob was talking about how NASA wants to be, Bob calls them anchor tenants, but it's sort of they want to start a space economy. I want to start an economy where companies are making money in space, and NASA wants to get that started to the extent to the extent that it can. So I love that. I think that's a good approach for NASA to take. And with respect to these laser pathfinders that these relays and stuff like that, I have just two quick questions. What are the wavelengths of these lasers? And second, what is the latency of the communication? David.
Okay. So what we're using is the near infrared, and it's 1550 nanometer range.
Okay.
And great benefit of this is that we can leverage the terrestrial investments and developments at those wavelengths. So then the latency. So it's a good trick question that I use sometimes on outreach things, is that I'm sending 100 kilobits per second over RF and 100 kilobits per second over optical. Which data gets there faster?
It's the same.
And the answer is it's the same. So they're both it's both the speed of light. So
Yeah.
what the laser helps with the latency part is that once you can send things at the higher data rate, then your latency for a volume of data becomes quicker.
I see. So one of the big issues for Starlink is this latency issue, but that's why they go to low Earth orbit. But you're saying because you can do so much more
That's right.
data,
That's right. So for real time, there's not like a significant advantage or an advantage to go to optical. But for if you're real time streaming, but if you've got your data file, like the full length HD movie of the astronauts exploring the moon, they'll be able to transfer that whole file much quicker over that higher data rate that laser enables.
Okay.
May I add one qualifier for that?
Okay.
I agree on the physics. The business model is a little different in the sense that if you are, as David pointed out, we have a customer who wants to do 17 hours of streaming video off the lunar surface.
Ooh, that'd be me.
Yeah. Okay. And that's actually on Eclipse lander. They are looking at terabits and potentially in overall volume petabits of data. But their business model is they want to stream all the way down into what would be the broadband distribution network on the Earth, and then put it up live, as close to quote live can be. And it's about 1,800 milliseconds roughly that it would take to get to that point. And if you're streaming, it's not a packet; it's actually going to be a stream. And so what they want to be able to say is streaming live now from the surface of the moon. And then what are they doing? Whether it's a Coca-Cola commercial, it's a Super Bowl, or something else, they have a value proposition to that. The difference is RF is wonderful for connectivity, but optical is wonderful for content. And that's it. I mean, you can get 4K, 50 frames per second on optical. You can even juice it and go 8K, 100 frames per second. You're not going to get that with RF at that distance. You're going to have to buffer it somehow, somewhere. You're going to have to, like Laddie, but you had, what was it? The Bill Nye the Science Guy. You guys did a program for Bill Nye the Science Guy back in 2013. There's Bill Nye broadcasting from the moon, and yet it was store forward, buffered, and then shot back down and broadcast. That was really cool. And what's funny is, and I think the future is, no one knew the distinction between him broadcasting from the moon or from his studio on the Earth. So you literally brought the moon right onto, you closed the distance and brought it right into the home. That's really cool.
Okay, so let's get to Raj's question. What's the maximum range that we're talking about with these laser communications systems? Can we do a deep space relay?
Yes. So certainly the range becomes limited by how many photons you can get from the distance. So the signal power falls off. It's like a square law. So there's that power factor, and then the real big challenge with the optical links is as you get that narrow beam, then the pointing becomes a real challenge. And it's a fascinating thing with RF versus optical. When you go farther away, then right now, so for example, Voyager is 21 light hours away, right? So the problem is that if you had your optical comm system there and you received the signal from Earth, then the beam, when you transmit back, you can't transmit back the direction where you got the signal from. You have to lead it and know where your target is going to be, because it's going to be out of the footprint when you do it. And I started with the Voyager example where of course that makes sense because it's moved 21 hours. But just the problem of going to Mars, where it's 10 minutes or 20 minutes, then already the relative location of the moon and of the Earth and Mars has moved 10 minutes worth, and they've rotated some, and all of that will move the transmitter and the receiver out of each other's beam widths. So you have to do this thing that's called point ahead. It's equivalent to like a football quarterback throwing the pass to where the receiver is going to be, instead of where they are when they throw the ball. So that is so that's the power level and that pointing are the big challenges for the distance.
So are you testing this now with DSOC, with the SECI thing, or no?
Yeah. So DSOC is going far enough away that these point ahead effects are more significant than anything we're seeing there with LCRD.
Yeah, I can't imagine how to doing that. So Raj also wants to know if an object passes through the laser, what happens to the data? So if it gets blocked in some way, like a rogue moon. I don't know.
So there'd just be a dropout for whatever the period. Assuming it's an opaque to the laser, there'll be a momentary dropout, and then maybe there's some channel coding or interleaving or something that it might not have any effect. But if it's a long enough outage, then there'll just be a dropout.
Okay. Dan from Canada wants to know what would power this equipment? Solar and battery? You get it up in orbit, what's going to be the power source? RTGs?
Well, it's really whatever your spacecraft's power source would be.
Okay.
So
plug
for
it in.
LCRD, we're on a spacecraft that has solar power. When you go to places where solar power is not available, then you have to use whatever you can.
Just give it juice, right, of some kind. Okay. Well, to what extent can the cislunar environment and Earth? Well, first of all, I think cislunar is kind of a big term, right? It covers a lot of territory. Can the infrastructure that's being built in cislunar space share infrastructure that exists on Earth? Like, I know Starlink isn't designed for it, but something, let's say, like that in the future comes along, where everywhere on the planet Earth has internet via this shroud of satellites that's set up. Is there any way that could be tied in, or are there any plans to share infrastructure between Earth and the moon, communication-wise?
I think it's probably inevitable, and I was going to say it sort of starts to show up in Bob's pictures. So I think, Bob, you ought to answer this one.
Yeah, I think the principle behind Bill Nye the Science Guy that we mentioned earlier is the same thing that we're doing, and that is we're trying to pull Lumen, Orange, other carriers to look up and connect to infrastructure in space, and then through relay to the moon, and you have compatible infrastructure on the lunar surface and then on the Earth. And then you use software to basically they're almost all autonomous systems now, so you use software-defined features and cloud features where someone who's at a NASA center can investigate what would be in a lander payload, visualize it, manage it remotely, and do it right through their Lumen connection they have every day. So Lumen is selling what would be lunar services, and those the clips are basically providing connectivity back to the Earth. So you're really growing. You've got to grow this infrastructure together. It's happening in LEO, But now you want to do it in Cislunar.
Yeah. Okay.
And I got a picture of that.
Okay,
Yeah,
go ahead.
Okay.
I'll just make this comment from Chris. He says much of the latency comes down to protocol, not distance. Is that really true? Distance isn't a factor for latency?
So it depends on the distance, right? There's a certain point where the distance will dominate. But for LCRD, we have the geo distance, but we also have interlevers to help with the data loss. So those interlevers could basically buffer a second's worth of data, shuffle it up, transmit the data, and then you kind of unshuffle it on the other side. And it does great to take care of like burst errors that happen going through the atmosphere, but you get this latency because you've done the interleaving. So go ahead, Bob.
Oh, I was going to say this is actually a very important part. We did a study for NASA a couple of years ago on relay, deep space relay, and one of the issues dealing with protocols is really starting from: do you want to replicate the TCP type infrastructure we have on the Earth? Do you want to do that on the Moon, where everyone goes to kind of a NAP or a central point or an NII, and then they're routed based on their IP number to where they're going to go? Or do you want to do it direct? And space affords you the ability to go more direct than necessarily go to what would be these transfer points. So that's where protocol does contribute to latency, but more importantly, where architecture contributes to latency. So what NASA's done is reached out to the private sector, and the private sector will build it differently, I think, on the Moon than they will on the Earth. But it'll have the same result. There'll just be more efficiencies built into it.
Okay. I'm sorry, Shantanu, go ahead and
yeah, I wanted to sort of ask for both our members here, both from Bob's perspective, especially on the business and commercial side, and from Dave's perspective, more on the scientific. We normally tend to think about all the communication needs and the data downloads primarily in terms of down to earth or back to earth, or the downlink part of it. It'll be great to hear both from Bob as well as from Dave. For the uplink part, what are the driving factors? Are these like health information for potential astronauts, or file uploads for additive manufacturing kind of things, or any other things? And same both from the business perspective, business case, as well as from technical and scientific or NASA kind of perspective. Bob, you want to go ahead, or and then we'll go to Dave.
Yeah, we did in order to finance the company and also validate it as a business, we did a customer survey back in 2020. We announced it in June, and we did the survey thanks in large measure to the Space Foundation. They gave us access to about 4,000 members, and we threw out what was a questionnaire to them. The result was really enlightening in a sense that what customers were looking for was what I would, in common sense, was layering: landers first, physical infrastructure second, coming from the Earth. So part of that study was healthcare and monitoring astronaut, basically life cycle and that sort of thing. So from that, we extracted the numbers that we thought were going to be the drivers of our service. And we found that we extrapolated from the ISS the numbers they use for their RF activity on the ISS. We just said, okay, they're going to do the same thing on the Moon with maybe a little bit more. And we came up with numbers. And both service lengths of 100 megabits per second and other types of consumption numbers. And we estimated a 10 gig volume, our service capability for Artemis, broken into sections, similar to the way it is on the ISS. Then we looked at the private sector, and the private sector wanted 1 to 10 gig optical units and 100 gig to 200 gig megabit RF units. Now, when you do all that math, you apply it to what the services are, and then you can extrapolate what would be your market, and then you break it into sectors of the market: healthcare, industrial development, robotics, content delivery, TT&C, emergency communications, etc. That pointed us in a way that you had to have a system that was as good going up as it was coming down. Now, Dave can address, at least on the optical side for sure, there are challenges on maintaining that link going up. So I'll give Dave the hard part.
Yes, so Dave, go ahead. I mean,
that's right. So the optical uplink is much harder because well, especially when you're coming from Earth, because you hit the atmosphere first, and then things get kind of scattered and things. So it's much harder to do the uplink direction. And so, for example, the LLCD, we were able to. It was designed. We did 622 megabits per second from the moon, but only 20 megabits per second up to the moon, which is still like a huge number compared to what's nominally done to the moon, in previous missions. But you can get a feel for the challenge going in the uplink direction. And back to that question. So what? So certainly when there's the human spaceflight element, and that's where and there's humans on both ends of the link, then that's where you get the more symmetric data requirements, because they're exchanging, voice, video, but just kind of the other human activities. But what we've also seen just with our robotic missions over the years is that as the computers and the programming gets smarter, then there's uploads of data sets, updates of programming, uploading tables, and there's other things, and when things go forward, if you start to have space platforms sharing data with each other to do other calculations or to work cooperatively, then there'll start to be more data needs going to the spacecraft as opposed to it being more asymmetrical and coming from the spacecraft.
Okay, yeah, thanks, Dave. Any questions from the audience, Tony? Or
well, we're actually out of time.
okay.
So I would, but I think we've gotten to most of them. I'll just do a real quick check. All right, here's one more, real quick. How much does the LCRD weigh?
Oh man!
And what are the power requirements? He asked two questions. You have time, or can you just do a quick
go look on the website. I don't want to do it offhand.
Okay, all right.
Memorized for all the press stuff, but I've already forgotten exactly what it is, so I don't want to.
Okay, that's
I will
fine.
say that when you see the numbers, remember that this, even though we just launched, it's older technology, and things can be actually integrated and be lower power and size than what we just launched.
Okay, well, gosh, this stuff really turns my crank. So I'm glad you guys are out there working on this, and I have a bunch more questions, but we need to cut it off here. I want to thank you guys so much for joining us and talking. Shantanu Gupta, he's from Aerospace Corp, Chief Engineer for the Optical Communications Center. David Israel is from NASA Goddard. He works on the architecting of all these communication projects. And Robert Brumley, he's the co-founder and chairman of Comstar Space Companies. Thank you all for taking time out for being with us. We will be back next month. The American Astronautical Society and I are working on the third Thursday of the month, so we will be back. So please check us out. I will post invitations to the events once we figure out what they're going to be and get everything finalized. So we'll see you guys next month. Thank you on behalf of the American Astronautical Society and our guests. Thank you so much for watching. I'm Tony Darnell, and
Thank you all.
Yeah, see, and keep looking up. All right.